François.
François Waldoir, donc ingénieur senior à l'UDF-R&D et aussi co-encadrant.
Et enfin, c'est pareil, il n'a pas besoin de présenter, mais il va se présenter quand même, Jimédo. Eh bien, nous sommes tous là pour écouter votre bel exposé. Vous avez 45 minutes.
Merci. Okay. Donc, ma présentation sera tout du long en anglais. Okay, so hello everyone, my name is Bacquaert. I'm going to present the main results of my thesis entitled Behavior of Geomaterials from the Modeling and Safety of Geotechnical Structures under the collaboration of Électricité de France, Sorbonne Université, and École des Ponts Paris-Tech. To start this presentation, I would like to position this thesis at Électricité de France, in which we aim to study some infrastructures like dams or dikes, which are concerned with mechanisms of failures like liquefaction, settlement, and sliding, which can also, on the other hand, be observed at the laboratory with experiment on granular soils. The methodology which is used in order to predict and thereafter to avoid these mechanisms of collapse is to carry out numerical simulation with the finite element method, which need a constitutive model to describe the phenomenology of granular soils. However, in our current practice, the more the phenomenology we want to describe is rich, the more the formulation of the model is complex, which raises difficulties both at the level of the numerical implementation as well as for practical and convenient use. So the aim of this thesis was to find a compromise between phenomenology, robustness, and simplicity of the constitutive model. We thus contributed by designing a constitutive model for granular soils which is thermodynamic based in the context of generalized standard materials. At the same time, the model was validated with experimental data in order, in parallel, to propose a methodology of calibration for the parameters which had been involved. The model finally has been made available in the finite element software Codaster used at EDF. A final contribution was to dedicate a framework in order to predict both regimes with strain localization and softening for the constitutive model. In this presentation, I will be focused on the first and the fourth of these contributions. The outline of the presentation will be to give some concise experimental elements about the behavior of granular soils in order to introduce a phenomenological model which is named the modified Campley, which was taken as a starting point in order to design a new one. Indeed, in order to improve its predictive capabilities, I'm going to propose an extension of this model. The second part of the presentation will be more dedicated to the question of regularization, in which we are going to introduce the gradient of a cumulative plastic strain in the dissipation potential of the model. At the end, this approach will be applied to the modified Campley. To start with some experimental elements about the behavior of granular soils, we can first be focused on loading conditions which lead to strain localization and softening. Here you can observe a triaxial compression performed by Edward Ando on a dense granular soil, which is characterized by an initial low porosity. During this test, you can observe a softening behavior of the resultant force until a residual level, and in parallel, the emergence of a localization pattern within a shear band. Inside this one shear band, you can also observe that there is a higher level of porosity in comparison of the rest of the sample. This shear band is thus said to be dilatant. If we are also concerned with the experimental behavior of other granular soils which are characterized by other porosity level, what can we observe during the same triaxial compression is a more pronounced softening regime for dense granular soils. In comparison, for samples which are looser with the initial higher level of porosity, there is more tendency of hardening and a maximum stress equieffective one which is lower too. In parallel, there is also a change in the evolution of the volumetric strain. The more the sample is initially dense, the more you can observe an increase of the volumetric strain, which means this is synonymous of dilatancy, an increase of the volumetric change. At the same time, it's interesting to note that the main mechanism of irreversibility we can observe is plasticity, by the presence of a large amount of residual strains at each unloading phases. In order also to complete this information, we can consider cyclic tests, which are going to show a hysteretic behavior during this kind, which is a compression extension, and the second one, which is a shear test. They mainly show that there is an onset of plasticity very soon after there is a change of the direction, the loading direction, which in the end means that the domain of reversibility of granular soil is quite small. In order to model all these experimental elements, phenomenological elements, there is one model which was designed in the 60s at the University of Cambridge, named the modified Camclay, which can be formulated within the assumption of the generalized standard material, the GSM. In this methodology, we can classically first define a free energy psi, which is going to add next to the elastic part an energy which is stored by hardening. This one is piloted by the volumetric part of the plastic strain. Thus, it allows us to define PC, which is named a consolidation pressure, which is the force dual to the epsilon Vp. Next, in order to derive the law of evolution, we can define a plasticity criterion, F, which in its canonic form is an equation of an ellipse in the space of the two first stress invariant, sigma h, the equivalent 1, and sigma m, the hydrostatic part of the stress. And in this equation, you can observe two mechanisms of hardening. The first one comes from PC, the consolidation pressure, which acts like a back stress, which therefore is going to predict a isotropic a kinematic hardening along the hydrostatic axis. Next, you can also observe the state dependency of the plasticity criterion by the volumetric part of the plastic strain. It's going to be involved in the evolution of the radius of the domain of reversibility. So this predicts isotopic hardening. The combination of these two is reflected on this figure for different value of the volumetric plastic strain. The more it increases, the more there is a shrinkage of the domain of reversibility. One state of particular interest is the one which is located at the top of the ellipse, which, according to the flow rule, which is normal, predicts isochoric plastic flow. At this stage, you have a linear combination between the equivalent stress and the hydrostatic stress by a friction coefficient named m. In the context of granular soil, this one is so-called the critical state. It must be emphasized that in this formulation, we are consistent with the GSM because we can define a dissipation potential which is state dependent. This state dependency comes from the involvement of the volumetric part of the plastic strain, the hardening variable, in the radius of the ellipse. So the isotopic hardening of the model is triggered by this state dependency. And in the case there is an increase of the volumetric plastic strain, a dilatancy, there is a softening by the decrease of the size of the domain of reversibility. When we compare the prediction of this model with experimental data, we can, on the one hand, be satisfied with this prediction for loose granular soil. On isotropic compression, for which the nonlinearity of the irreversible response can be captured, as well as during triaxial compression, the right ultimate and maximum equivalent stress for different confinement level sigma 3. However, the model was not designed to predict the behavior of hysteretic behavior, as well as to be realistic with the softening evolution of dense granular soils. In this case, the maximum equivalent stress is much overestimated, and there is a slope which is too acute during the softening regime. So, in a brief, this model, the MCC, has the benefit to unify in a quite synthetic formulation phenomenological aspects of granular soils, dilatancy, positive hardening, and softening, within a formulation which is consistent with the GSM by the help of a state dependency in the dissipation potential, or equivalently in the yield criterion. However, the two previous limits about the overestimation of softening and the lack of irreversibility representative or hysteretic behavior led us to consider an extension of the model with the help of two nonlinear hardening mechanisms. Our originality, which is going to be presented, lies in the fact that we never left out the assumption of the normality rule by this extension. In the manuscript, you can also find a use of nonlinear hyperelasticity, which allows us to add pressure dependency on the elastic moduli according to a procedure proposed by Emmanuel Bourgeois. So, in order to give the main ingredients in order to extend the MCC model, we are going to follow the same methodology as it has been just presented before. In order to, we consider once again the definition of the free energy, psi, which is going to add next to the MCC contribution two new ones which are controlled by two internal variables, chi, a new one which is a scalar, and alpha, a new one which is a tensor of order 2. So, from this extension, we derive two new other forces, respectively S and X, related to chi and alpha. Next, in order to derive the new evolution, the new law of evolution, we decided to define the domain of reversibility by keeping just one yield criterion for simplicity. In this extension, we modify the definition of an equivalent stress, Dx, which involves from now on the two forces S and X. In this extension, we were quite inspired by other approaches in order to model similar elements, but for other classes of materials. The first was motivated by a work proposed by Nelly Pointe and Silvano Erliche, who tried to introduce nonlinear hardening by going beyond the linear kinematic one. In their approach, in the yield criterion, the equivalent stress is replaced by a combination between the deviatoric part of the stress and the new force X. Here, in the first term, X would play like a back stress as for kinematic hardening. However, the other term, which involves a new parameter R, allows us to introduce nonlinearity in this hardening. This is quite interesting and compulsory if we want to be able, as for the Camp-Clay model, to predict an ultimate state for which there is no evolution of the equivalent stress. Our second modification was motivated by the wish to be more representative of dense granular soils, about the softening evolution. In order to, we decided to introduce this force S at two locations in the yield criterion, so that in the end it is going to predict the scenario which is displayed on this figure. Starting from a very small initial lead surface, the evolution of the internal variable, chi, is going to produce a positive homothétic transformation until the original MCC surface. By doing so, we are thus able to predict an onset of plasticity for stress levels that are far lower than the one which would have been predicted by the MCC model. At the end, it must be once again emphasized that by doing this extension, we have never left out the assumption of the GSM, since in particular, next to the plasticity criterion, we can define a dissipation potential phi. In this one, you can observe once again that we have kept the same state dependency of the volumetric part of the plastic strain, which comes originally from the MCC expression. All in all, at the end, two new parameters have been introduced in the hardening in order to keep it quite simple and manageable. Going back to the experimental comparison, you can see again with the blue lines the MCC prediction with the experimental data and some of its deficiencies. Next, our proposition in order to extend the prediction of the Camp-Clay model allows us to be more predictive both with regard to the hysteretic behavior during the shear test, cyclic ones, as well as the maximum equivalent stress and the softening evolution during triaxial compression of dense granular soils. You can observe that between blue and green line, you have the same asymptotic behavior. They have the same stress level. This reason lies in the expression of the hardening which have been introduced, which are nonlinear. However, up to now, we haven't said a word about how this model, both the MCC and its extension, can be integrated numerically and about its robustness of properties of robustness. To give a few words about this and how it is used in Codester at EDF, usually this finite elemental software is going to solve an equation of an equilibrium by making zero some residual at each time step with respect to the displacement. As for the integration of the constitutive equations, they are nested at the material points and are solved by the source code generator M front, which role is to update the stress sigma, the internal variable A, as well as to compute a consistent tangent operator. In order to perform this step, we followed an incremental variational approach of Ortiz and Seignier, for which the stress sigma is the derivative of an incremental effective potential, W, which is the optimal value of the incremental total energy potential minimized by all the internal variables, which sums the contribution of the free energy and a consistent approximation of the dissipation potential. This approximation, which is detailed in the chapter 3 of the manuscript, relies on a quadratic approximation with respect to the state dependency of the dissipation potential, which allows us at the same time to keep it convex. At the end, following this approach, we also have a symmetric tangent operator, consistent tangent operator, which in all our numerical experiments favored a lot the properties of robustness at the structure level. In order to illustrate it, we consider a biaxial compression test, which showed, according to the constitutive equations, to softening. You can observe in this case that even after the positive half-Denis regimes, the computation went to the end, even in the presence of strong softening and localization. We must say that in opposition, a non-variational resolution of the constitutive equation, which is sometimes advanced in order to solve, for instance, the MCC model because of its state dependency in the dissipation potential, was able to go to the end of the calculation. However, you can also observe that up to now we have not solved the issue of mesh dependency, since, for instance, a cumulative plastic strain, which takes into account by a quadratic interaction the deviatoric part of the plastic strain and the volumetric one, depends on the mesh size of use, as you can here and there observe. So far, we used one framework which is available in Codaster in order to regulate the constitutive equation of the model, which is based on a second strain gradient model, which is discussed among others by Romeo Fernandez. The main idea of this framework is to enrich the equation of equilibrium, or equivalently the internal virtual principle, by extra terms which are supported by the gradient of the total volumetric strain. However, using this approach, we were quite mixed. On the one hand, for sure, it helped with also the use of a variational resolution to update the internal variable to get calculations to the end, even in the presence of localization and softening. However, on the other hand, we were quite disappointed in order to obtain mesh-independent results, as it is here illustrated with the evolution of the force with the displacement on a biaxial compression, even with the refinement of the mesh size. So, in order to bypass this difficulty, we tried to explore another approach of regularization, which will going to be based on the cumulative plastic strain itself. Actually, this approach is going to be implemented in is going to be exploratory in the sense that it is going to be some other numerical tools are going to be explored. So going back to our proposition, as it has been said in the line of GSM, we are going to use the gradient of one internal variable. And this one, which is going to be selected, is a cumulative plastic strain. And in general, this is going to be a positive increasing quantity with no maximum finite value. Therefore, in order to regularize this quantity, we are aware of some difficulty if we just regularize it, for instance, with the square of its gradient in the free energy. One consequence is the phenomenon known as the spreading of localization bond, as it is illustrated on the left with the fact that the size of the bond is going to increase during the loading. We were also, however, aware of some quite sophisticated attempts in order to regularize this otherwise by Jean-Michel Serrer or Mohamed Abatour, in which they involve either a decreasing regularization parameter with the cumulative plastic strain itself, or by regularizing a saturating function of the cumulative plastic strain. At the end, these two expressions are going to predict the scenario which is displayed with the dotted line on the right, in which more and more there is plastic strain, more the increment is going to be located on a bond of smaller thickness. our approach, which is going to be presented, was quite different. We tried to explore the possibility to introduce the gradient of a cumulative plastic strain, no more in the free energy, but in the dissipation potential. By doing this choice, we have to have some constraint about the way it must be involved. So, in order to be quite general, we consider A as a tuple of internal variables which consider as one of them a cumulative plastic strain. In order to define a model with gradient of plasticity, we take, for the expression of the free energy psi bar, the same expression as for the local one, which means that there is no involvement of gradient of plastic strain. Next, the dissipation potential phi bar is going to add next to the local part a new contribution in a function pi, which will in general takes both arguments at the rate of the cumulative plastic strain and its gradient. To this function, we are going to ask it two conditions. The first one is to be one homogeneous in order to be consistent with rate-independent plasticity. The other one is to say that during homogeneous response, this model with gradient of plasticity is going to predict the same response as the model without gradient of plasticity, the local model. In particular, this condition allows us to have the same initial yield stress. One example of function which has been studied in the thesis is this maximum potential, which is defined in general by two independent parameters, sigma infinity, a stress-like, and L infinity, a length-like. The reason of this study is that we can have analytical solution with this function, which are going to be explained. In order to introduce this solution, we consider a one-dimensional study and a local constitutive model, which is defined by the following equations. In particular, in this one, the softening comes from the decrease of the current yield stress, starting from the initial one, sigma 0, with the cumulative plastic strain, according to the softening parameter named B. In these curves, you can observe for an homogeneous response over a bar interaction, the evolution of the stress sigma with the blue line and the evolution of the dissipated energy d bar according to the displacement which is prescribed. And as it has been stated just before, we can find the localized solution with the help of this gradient maximum potential pi. So the following properties hold for a sigma infinity larger than the initial yield stress. First, on the right, we have exponential profiles of the plastic strain, which decrease is piloted by the length L infinity involved. Next, second, the evolution of the stress with the displacement is predict the more the ratio between L infinity and the length of the bar is small, fragile evolution during the softening regime, as it is here displayed in the case of non-snapback at the end of the elastic regime. Third, the property we observed when looking at the evolution of the dissipative energy was the following. For a fixed level of the displacement applied, we observed that the dissipation is dependent of L infinity, which was involved. However, when we would go to the limit and the plastic strain or the loading would go to infinity, we observed that the final dissipation is no more dependent of L infinity, but reach the same value as the ultimate dissipation of the homogeneous response, so that it is proportional to the bar itself. It's quite interesting because in a way, it reminds us that this regularization approach for plasticity is not quite the same of regularization of damage, in which we could expect that the final dissipation would involve one parameter, length-like, for instance, which would act like a regularization one. In a brief, our approach has been thus to involve a cumulative plastic strain, a positive increase in quantity with no finite maximal value, not in the free energy, usually by a quadratic term, but in general in the dissipation potential by this function homogeneity 1 pi. The previous analytical solution showed us an exponential profile, so that it means that this plastic strain bond is going to keep its shape at each time step, and so this is an evolution which is stationary. In fact, when we try also other expression for defining this function pi, as for this one which is going to be named a quadratic on linear potential, we also observe quite similar property of stationarity with the evolution of the plastic bond along the loading. More general, these two examples can be embodied in more general other ones which are defined by semi-norms, for instance with an index m larger than 1. And in comparison, our approach, which relies on the dissipation potential, allows us to have plastic bond which can be much more confined in comparison with the more usual regularization by the quadratic term in the free energy. Thus, after having proposed this approach of regularization in the dissipation potential which has been applied in one dimension, I will be able to apply it to the modified Kamklé model itself, which was taken as the starting point at the beginning of the thesis in order to design a new one. To do so, we go back to the definition of its free energy and its dissipation potential. The first, psi1, takes the same expression as for the local model without no involvement of gradient of plasticity. The new definition of phi bar, the dissipation potential, adds next to the local contribution the function pi, which takes the plastic strain and its gradient, the rate, as argument. You can observe that in this definition, you have the definition also of the cumulative plastic strain itself, as it was previously proposed, which takes into account by a quadratic interaction the equivalent and the volumetric part of the plastic strain. In order to solve this model with gradient of plasticity, we rely also on a minimization of an incremental total energy functional, which at the level of the structure minimizes according to the displacement and the internal variable seen as field, both the free energy and a consistent approximation of the dissipation potential. In general, this minimization will be state dependent, that is to mean that we minimize the functional j with respect to the displacement and the internal variable, which is dependent of the volumetric plastic strain. This state dependent is a consequence of the state dependency of the dissipation potential of the model. So, inspired by a fixed point strategy which was proposed by Christian Krabenhoft in order to design a variational resolution of the Kamklé model stress-based and with no regularization approach, we also use the same strategy, which consists at each time step to minimize j over a sequence of iteration in which we iterate over the state dependency by the volumetric plastic strain at the end until we reach a tolerance criteria without a prescribed value. As for the numerical tools which are used in order to solve this problem, we heavily relied on conic programming and convex optimization solver, which have been implemented in the finite element method in the library Phoenix by Jeremy Blair. So to present the following applications, rely on the fifth parameters in order to define the local constitutive model parameters of the Kamklé for elasticity, friction coefficient, and for the evolution of the consolidation pressure, PC, which acts like in kinematic and isotropic hardening. The first example is the stretch in plane straight conditions of a specimen in which the section has been slightly reduced in the middle in order to trigger their localization. The function pi will be after that precised according to the previous expressions which have been presented in one dimension. So the first expression takes this maximum gradient potential, which for sigma infinity takes the initial value of the consolidation pressure, in this case, a local constitutive model parameter, and arbitrarily L infinity is 10 mm. Here, in the sample, on a vertical line, you can observe in the center, the cumulative plastic strain, which is not located over one mesh size, and on the right, the evolution of both the volumetric and the equivalent plastic strain during the loading. You can observe that we find again the exponential profiles of the one-dimensional test in which the length of decrease is piloted by L infinity. For the other possibility also which was introduced in the one-dimensional study, a quadratic or linear gradient potential, we find once again there is no concentration over one mesh element, and obviously we have no more with here the dashed line, the exponential previous profiles, but in red and blue ones, volumetric and equivalent plastic strains, which are more close of cosine or hyperbolic cosines. To give some information about how it can give efficient results, we can, on the one hand, on the left, look at the evolution of the force response along the displacement for different mesh sizes and different value of L infinity. In this case, we have mesh independency with quite satisfaction, even in the presence of strong softening regimes. On the other hand, the figure on the right is quite interesting in order to observe how it is costly in order to perform at each time step this fixed point iteration strategy. What we can observe is that it is mainly costly and involved at the onset of softening and at the onset at the same time of localization, about a displacement of 0.5 mm. After that, it doesn't cost anything to use this fixed point iteration strategy, since after one or two of them, we have reached the tolerance criteria which have been prescribed. This is interesting because thus it can be compared to the performance of a regularization more usual by a quadratic term in the free energy. In this case, you can observe that this fixed point iteration is far less efficient, since even after the onset of the softening regime, we seem to need a lot of iteration in order to get the same stationarity criterion. This kind of erratic evolutions were quite explained when we took a look at the ISO values of the increment of the plastic strain at each time step. It seems that we switch between two modes of localization. On the right, something which would be expected, a symmetric one around the middle of the sample, or other hand, a kind of a localization with two bonds at both extremities with an elastic unloading in the middle of the sample. This is the cause of the different behavior of the different numbers of iterations, either a large amount or a low amount, between these two kinds of localization observed at each time step. At the same time, during the evolution of the force with the displacement, we also have this erratical evolution even by changing the mesh size of use. Finally, as a second application, we are going to consider a test which is more close of real one at the laboratory performed by Patino Ramirez, in which a cavity is surrounded by a dense granular soil media, and by extending the volume inside this pressure meter, we observe a softening evolution, which means that the pressure in the cavity is going to decrease as well as the volume is going to increase. In parallel, by tomographic observation, we can look at shear band inside the sand granular media, in which you also observe an increase of the porosity. This is exactly the same pattern of localization as presented in the introduction, a dilatant shear band. So in order to model with much simplicity this problem, we consider still in plane strain conditions a borehole which is subjected at the outer edge to a radial pressure and to mean displacement at the inner edge, so that it allows us to increase the cavity, the volume of the cavity, while keeping the same aspect ratio between the external and the internal radii, and by changing the internal radii, we are thus able, with the Kamkley model with gradient of plasticity, to model size effects. These one are illustrated for different internal radii ranging from 1 mm to 1 cm. On the first line, you can observe the final ISO values of the equivalent part of the plastic strain, and on the second one, on the volumetric part of the plastic strain. On the left, we have almost axisymmetrical solution for the smallest borehole. Nevertheless, for the largest one, with a realistic value of 1 cm for the internal radius, we observe a sharp shear band starting from the inner edge, crossing the sample until the outer one. At the same time, and as in the experiment, you can observe that there is an increase of the volumetric part of the plastic strain inside this shear band, which is the consequence of the fact that the Kamkley model is predictive of softening in case of dilatancy. Now it's time to conclude. Going back to our contributions, we propose to design a constitutive model for granular soil, taking as a starting point the Kamkley model. By doing so, we have been able to understand in the GSM framework it was predictive of both kinematic and isotopic hardening. The last one is the consequence of the state dependency of the dissipation potential, and in case of dilatancy, an increase of the volumetric plastic strain cause of softening. However, in order to improve its predictive capabilities for hysteretic behavior and for the softening of dense granular soils, we propose an extension which is based on nonlinear hardenings, which are associated and consistent with the normality of the flow rule. By this formulation and this extension, we thus have been able to propose a resolution which is based on an incremental variational 1, which all along the numerical experiment in this thesis allowed us to have far better properties of robustness in comparison of a non-variational approach, which is sometimes advanced in order to solve the constitutive equations of the model with state dependency in the dissipation potential. Our second contribution was motivated initially by the fact that controlling the volumetric strain or the volumetric part of the plastic strain didn't seem to be enough in order to regularize the constitutive model. So we introduced more generally a cumulative plastic strain, a positive increasing quantity with no maximum ultimate value, not in the free energy by a standard quadratic term, but in general in the dissipation potential by a one homogeneous functional pi. The solutions we observed, numerically solved with conic programming, showed us an efficient resolution in order to have mesh-independent results, as well as to have a nice control of plastic localization band in comparison with this regularization by the square of the gradient. As for the perspective next to the thesis, on the one hand, in the industrial context, the extension of the MCC model will be used in more geotechnical applications on more realistic structures like dams and dikes. So far, we have focused on simple calculations, but since we have kept our model quite synthetic with a few internal variables and robust because it can be integrated within a variational incremental resolution, we can be confident about this transition of scale. Another perspective will be to analyze in more depth the current methodologies in Codaster in order to regularize the constitutive equations of the model, since up to now just one of them have been used, a second train gradient. As for a research perspective, one of very high interest will be first to formulate the constitutive models in the context of poroplasticity in order to take into account water saturated granular ones, since so far we have been focused on dry conditions. In this extension, we are going to extend the constitutive equation of the skeleton, and from now on taking into account the fluid equations, like for instance by extending the dissipation not by just the skeleton part, but the one by the fluid due to viscosity. By doing this approach, we can also rely on a variational resolution which has very similarity with what can be found in thermomechanics. And in particular, we can also dedicate an incremental scheme. Finally, a perspective of very general perspective will be to apply and to adapt the modeling elements, nonlinear hardening or gradient plasticity in the dissipation potential in the modeling of other classes of materials than granular ones, for instance, like to regularize ductile fracture for porous materials. Thank you for your attention.
Il y aura des applaudissements encore plus forts, mais plus tard. Merci en tout cas pour cette présentation d'une grande clarté. Donc, très bien. On va passer la parole au rapporteur et je commence par Pierre Désolé.
Merci.